This video is designed to introduce you to the concept of reaction types. By viewing this video, you will become familiar with 5 common types of chemical reactions, as well as how to recognize the type of reaction you are dealing with when presented with a chemical equation. There are a few things to remember before we begin looking at reaction types. This is an example of a balanced chemical equation. We have already learned about naming and formula writing for chemical compounds, and you can see evidence of that here with the correct use of symbols and subscripts for each component of the equation. In this equation, I have used green to represent the reactants or starting materials, and blue to represent the products or materials that are created as a result of this chemical reaction. Notice the use of plus signs used to separate each chemical formula in the equation, and that an arrow is used to separate the reactants from the products. You should also notice the 2 coefficients in front of NABR and NaCl, indicating that 2 particles of each of these chemicals are required to balance this equation. Remember that a balanced equation is the way that we represent how the law of conservation of mass is true. All of the atoms present in the reactant particles must be present and accounted for in the particles of product. We can't destroy atoms, nor can we create new ones out of thin air. Learning to recognize different kinds of chemical reactions is really just learning to recognize different patterns. Many common chemical reactions can be grouped into one of 5 reaction types, or patterns, according to how the reactants combine or what products are created. You will be expected to know 5 types of chemical reactions this year: combustion, combination, decomposition, single replacement, and double replacement. We will now go through each of these 5 reaction types in turn so that we can look more closely at the pattern of each type, as well as some more concrete examples. In a combustion reaction, a substance made of only carbon and hydrogen, a hydrocarbon, or what can also be called an organic compound, reacts with oxygen. The products of a combustion reaction are always carbon dioxide and water. In this general example or pattern, X represents a variable number of carbon atoms and Y represents a variable number of hydrogen atoms that together make up that hydrocarbon. If we look at some examples of different combustion reactions, you should notice that the only thing that differs between them is the specific number of carbon and hydrogen atoms in that hydrocarbon. Everything else stays the same. Oxygen is the only other reactant, and carbon dioxide and water are always the products. Because these are all examples of balanced combustion reactions, you may also notice that the coefficients are slightly different, depending on how many carbon and hydrogen atoms are present in the hydrocarbon in each example. You may already know that the word combustion refers to the burning or explosion of a fuel, a hydrocarbon, like methane, the fuel that powers our Bunsen burners in the chem lab. Think, too, of the internal combustion engine in a car. The gasoline you put in the tank of a car is the hydrocarbon, and when the engine is started, that gasoline is burned in the presence of oxygen to produce carbon dioxide, water, and the energy that powers the vehicle. Sometimes a hydrocarbon may be burned in low oxygen conditions. In this case, the combustion of that hydrocarbon may also produce carbon monoxide and soot or pure carbon as additional products, as shown in red. This is called incomplete combustion, and it is a potentially dangerous reaction due to the carbon monoxide that is produced. Carbon monoxide impairs the body's ability to transport oxygen from the lungs to the body's tissues. When the air you breathe contains high levels of carbon monoxide, it is possible to suffocate due to lack of oxygen, even though you are still mechanically taking air in that contains oxygen. Your body just can't do anything with that oxygen because the carbon monoxide gets in the way. This is why household furnaces, which run on combustion, are equipped with carbon monoxide detectors. It's also why you should never warm up a car in a closed garage. We're now moving on to the second kind of reaction, which is what's called a combination reaction. Combination reactions can also be called synthesis reactions, so you can feel free to choose whichever terminology you're more comfortable with. In a combination reaction, two or more substances combine to form one new substance. The number of reactant substances is always greater than the number of product substances in a combination reaction. We can represent this type of reaction using the pattern A plus B produces C, where A and B are two distinct reactants and C is the single new product formed. Please note that A, B, and C are not meant to be proper chemical symbols from the periodic table. They're just being used to represent different chemical compounds. If we look at this example of a combination reaction, potassium, or K, could be represented by A, Cl2 could be represented by B, and KCl could be represented by C. You can think of a combination or synthesis reaction like building a tower out of blocks. You start with separate blocks of each color, blue and red in this case, and then combine them to form a single product that's different from either of the starting components. In a decomposition reaction, one reactant breaks down into two or more products. Decomposition reactions are the exact opposite of combination reactions and can be represented by the pattern A produces B plus C, where A is the single reactant and B and C are the two new products formed. If we look at the first example of these decomposition reactions, HGO could be represented by A, Hg represented by B, and O2 represented by C. Because decomposition reactions are just the opposite of combination reactions, imagine taking apart that red and blue block tower. In a single replacement reaction, also referred to as a single displacement reaction, an atom or ion in a compound is replaced by an atom or ion of another element. We will represent this reaction type using the pattern A plus BC produces B plus AC. Note that BC is an ionic compound made up of a metal cation, B, and a non-metal anion, C. A represents that other metal that is not currently part of a compound. On the product side of the equation, the two metals, A and B, have traded places. In this example, the reactant magnesium, or Mg, is represented by the letter A in our pattern. The reactant HCl corresponds to Bc in our pattern, where B is the hydrogen ion and C represents the chloride ion. On the product side, hydrogen, or H2, matches up with the letter B, and MgCl2 corresponds to AC. A good analogy for a single replacement reaction is someone cutting in on a dancing couple. In this analogy, you have a couple, like BC, our ionic compound, and a lone dancer, like A, which represents our other metal. You can see how A, our lone blue dancer, has traded places with B, the yellow dancer, to create a different arrangement on the product side of the equation. Our final reaction type is the double replacement reaction, which can also be called a double displacement reaction. In this reaction type, the positive metal cations in two ionic compounds trade places, as do the negative non-metal anions. This type of reaction can be represented by the pattern AB plus CD produces AD plus CB. It's really important to note that on the reactant side of our pattern equation, A and C represent two metal cations, while B and D represent two non-metal anions. When these ions recombine to form two new products, A, a metal, must combine with D, a nonmetal, and the metal C must combine with the only remaining nonmetal, which is B. You will never see products made of two metals or two nonmetals in this type of reaction, as we are always dealing with ionic compounds in a double replacement reaction. In the example shown, we have two reactants, AgNO3 and KBr. Through this double replacement reaction, Ag from AgNO3 recombines with Br from KBr to form AgBr. The second product is created when potassium, or K, recombines with the polyatomic ion NO3. It may be helpful to think of the 4 ions in this example using the letters from the general pattern shown above. We can reuse the dancing analogy here. To make it work for double replacement reactions, though, we need to picture 2 couples dancing and then have them trade partners. That concludes the overview of the 5 main types of chemical reactions. As mentioned at the start of this video, your goal for this component of the chemistry unit is to be able to recognize the type of reaction shown when given a chemical equation. We will practice this skill in a number of ways together in class. Good luck!